Ice doesn't look dangerous at first. From the surface, the Arctic Ocean is a sheet of stillness, white, flat, silent. But beneath it is a liquid world engineered to kill mammals. Water this cold strips heat faster than air ever could. Muscles lose coordination. Breathing becomes a problem. Panic becomes automatic. And darkness is not a mood down here. It's a physical limit. Most warm-blooded animals avoid this place for a simple reason. It punishes every mistake immediately. And yet seals enter it on purpose. They don't just tolerate the cold. They dive into it, again and again, descending through black water where pressure tightens the chest, oxygen becomes a countdown, and the surface is no longer guaranteed. Today, we're diving into why seals choose to dive into the ocean's deadliest cold, how evolution turns a land-built mammal into a precision diver, capable of slowing its heartbeat, shutting down circulation to its limbs, and hunting in a world where the rules of survival are rewritten by temperature alone. Because in the Arctic, endurance is not toughness. It's biology so controlled it looks unnatural. Water does not forgive hesitation. Air can sting, it can numb, it can warn. Water does none of these. It takes.
In the polar ocean, temperatures hover around minus 1.8 degrees Celsius. Colder than fresh water can remain unfrozen, yet liquid because of salt. To human skin, that distinction is meaningless. Immersed in water this cold, heat drains from the body up to 25 times faster than in air. Muscles stiffen, fingers lose precision, thoughts blur, minutes pass, and coordination collapses. Stay longer, and the heart itself begins to falter. For a land mammal, this is not an environment to endure. It is an environment to escape. Heat always moves toward cold, and water is relentless in its efficiency. In air, a thin boundary layer of warmth clings to the skin, slowing loss. In water, that layer disappears instantly. There is no buffer, no pause. Cold presses inward from every direction at once. Most mammals respond with alarm. Blood vessels constrict in extremities. Shivering begins, a violent oxygen burning attempt to generate heat. Heart rate rises, energy drains faster, and eventually the body fails. Human survival time in near-freezing water is measured in minutes. Hypothermia does not arrive dramatically. It slips in quietly. Confusion, disorientation, collapse. Yet in these same waters, seals slip beneath solid ice without urgency. They do not shiver, they do not thrash, they descend. The ocean is not simply cold, it is structurally hostile to warm-blooded life. Unlike fish, mammals must maintain a stable internal temperature. Even in mild climates, that stability is expensive. In polar water, the cost multiplies. So how do seals survive immersion that would incapacitate nearly any other mammal? Insulation is the beginning, but not the answer. Most diving seals rely on blubber, dense, vascularized fat layered beneath the skin. It slows conductive heat loss and stores the calories required for prolonged dives, but insulation only delays loss. It does not stop it. Every dive becomes a negotiation between heat retained and energy spent. Seals routinely remain submerged for 30, 40, even 60 minutes. What prevents collapse? Circulation. As a seal descends, blood flow shifts, peripheral vessels constrict, flippers and outer tissues cool dramatically, approaching near freezing without damage. Core organs, brain and heart remain protected. This is not deterioration. It is design. By allowing non-essential tissues to cool, the seal reduces the temperature difference between body and water. Less difference means less heat lost. The thermal battle shrinks. Size strengthens this strategy. Many polar seals are large because evolutionary pressure favors bulk. Larger bodies lose heat more slowly relative to mass. Surface area works against small mammals in polar seas. The cold selects for volume. But temperature is only one axis of survival. The moment a seal slips beneath the surface, another limit asserts itself. There is no air. For humans, breath holding is temporary. Carbon dioxide builds. The diaphragm spasms. Panic intensifies. Seals do not panic. They descend, sometimes beyond 500 meters, carrying a single breath and a physiology prepared for scarcity. At submersion, heart rate drops dramatically, from over 100 beats per minute at the surface to fewer than 10 at depth. This bradycardia is conservation. Each heartbeat consumes oxygen. Fewer beats stretch the supply. Blood is rerouted. Muscles, digestive organs, peripheral tissues receive minimal flow. Oxygen-rich blood is reserved for the brain and heart. The mammalian dive response exists in all of us faintly. In seals, it is refined to its extreme. They do not react to oxygen decline, they anticipate it. Storage amplifies this advantage. Humans rely primarily on lungs. Seals store oxygen throughout their bodies. Their blood volume relative to size is high. Red blood cells are densely packed with hemoglobin. More remarkable still is myoglobin, the oxygen-binding protein inside muscle. Seal muscles appear dark because myoglobin concentrations are extraordinarily high. Muscles become oxygen reservoirs, releasing supply gradually during dives. This delays anaerobic metabolism, the shift that produces lactic acid when oxygen runs out. Seals tolerate lactic acid better than most mammals, but their strategy is not endurance through pain. It is delay through efficiency. Another adaptation seems counterintuitive. Many seals allow their lungs to partially collapse at depth. Under pressure, compressible air spaces become dangerous. Nitrogen dissolves into blood, risking decompression sickness. By exhaling before diving or allowing alveoli to collapse safely, seals prevent excessive nitrogen absorption. Gas exchange stops at depth. Oxygen delivery continues from blood and muscle stores. They shift from breathing with lungs to surviving on reserves. Lung collapse reduces buoyancy as well, making descent easier. Sinking costs less energy. Every adjustment activates automatically the moment cold water touches the face. But even these mechanisms would fail if metabolism remained high, so seals suppress it. Peripheral tissues cool. Movement slows. Muscle activity is rationed. Weddell seals can remain submerged for over an hour, hunting beneath ice in near-total darkness. They move slowly, efficiently, avoiding bursts of speed that waste oxygen. Dive duration adjusts dynamically. Shorter when prey is scarce, longer when conditions allow. Cold increases cost. Breath holding limits supply. Seals align physiology with both, but beneath the ice lies another constraint: darkness. Polar light collapses quickly, ice filters and scatters what remains. Beneath thick sea ice, the world becomes shifting shadow. Predators typically rely on sight. Seals rely on water itself. Their whiskers, vibrissae, form one of the most sensitive motion detection systems among mammals. Each whisker anchors into a nerve-rich follicle, capable of detecting minute changes in water movement. A fish does not need to be visible. It only needs to move. Swimming prey leaves hydrodynamic trails, swirling disturbances that persist in water. Seals can detect and follow these trails even after prey has passed. In laboratory experiments, seals accurately trace the path of moving objects through still water, guided only by wake patterns. Darkness ceases to matter. Many species possess undulating whiskers that reduce vibration caused by their own swimming. Self-noise is minimized. Sensitivity remains high. They glide, and the ocean speaks. But hunting under ice introduces another challenge. Air, undersea ice surfacing becomes navigation. Breathing holes, cracks, leads, or openings maintained by seals are limited. Miss the opening, and the dive becomes fatal. Weddell seals maintain breathing holes by grinding ice from below with their teeth. These openings become life anchors. They return to them repeatedly, even after deep extended hunts beneath shifting ice. This requires spatial memory in a three-dimensional environment that moves. Ice shifts, currents pull, visibility fails, yet seals navigate back to air precisely. They manage risk. Sound adds another layer. Under ice, low-frequency vibrations travel far. Seals vocalize, possibly to coordinate or maintain spacing. They are built to listen. And still, one constraint governs everything: energy. Freezing water drains calories rapidly. Every dive is a calculation between oxygen, heat, and food gained. Is the hunt worth the cost? At the edge of the polar ocean, seals reveal something deeper than endurance. They reveal a boundary. Their biology, oxygen management, flexible lungs, insulated circulation, whisker-guided hunting, memory of breathing holes, exists within balance, between possibility and limit. A seal can slow its heart, reroute blood, collapse lungs, navigate darkness, but none of this is infinite. These adaptations evolved under rhythms once predictable: seasonal ice, recurring prey, stable oxygen gradients. Now those rhythms are shifting. Sea ice forms later, breaks earlier, in some regions disappears entirely, breathing platforms vanish, prey distributions shift, oxygen patterns change. For a species built on precision timing, small disruptions compound. A seal diving under ice assumes stability long enough to return. A pup born on pack ice assumes that platform will persist. Hunting strategies assume prey will gather where they always have. When those assumptions weaken, endurance becomes risk. Seals have survived dramatic climatic shifts before. Their lineage is ancient. They are adaptive systems within limits. But where those limits lie remains uncertain. How much warming turns insulation into liability? How much ice loss undermines breathing strategies? How much oxygen variability compresses their margins? Seals do not conquer the ocean's deadliest cold. They negotiate with it. They do not overpower pressure. They yield to it. They do not fight darkness. They adapt to it. In imagination, survival looks dramatic: force, speed, aggression. In polar water, survival looks quieter: a slowed heartbeat, a measured glide, a precise return to air. Seals dive into lethal cold not because it is safe, but because it offers narrow advantage: fewer competitors, concentrated prey. Breathing access others cannot exploit. Their dive is not courage. It is calculation written into muscle, blood, and memory. How far can a mammal go before cold, darkness, and depth erase the advantage of being one? So far, the answer has been extraordinary, but as polar oceans continue to change, the question remains open. Beneath the ice, a seal slips into black water, heart slowing, lungs compressing, whiskers forward, balanced precisely between what life can endure and what it cannot.